Good evening, everyone. My name is Bodhisattva Das. I'm a security engineer at Rudra Cybersecurity, and thank you for coming to my session. Who gave the agent admin rights for securing cloud and AI machine identities? Before I begin, I'd like to do a quick poll. Please do a show of hands. Who here has ever given an API key, a GitHub access token, admin access to anything? Please feel free to raise your hands if you have. Well, I guess this is not going how I expected, but the gist here is we kind of don't know where we give access to. To get the stuff working, we initially make it overprivileged. We give it access to everything, but later on, we kind of don't know what these access tokens can do and what they can access. And that is the machine identity problem. Now, I'd like to talk about an incident from 2019. This was a breach for Capital One, a pretty large bank in the US. So they had a disgruntled former employee, an AWS engineer named Paige Thompson. She managed to steal records of over 100 million people. These included social security numbers, bank account details, credit scores, the works. The bank was slapped with a $80 million regulatory fine, and they settled for a class action lawsuit for about 190 mil. But can anyone guess how they detected that their data was breached? Well, they found out about this breach from a Twitter tip. That's right, a random tip on Twitter. It was not their SOC team, not their audit team. They were spending millions of dollars every year on complex security tools, but none of them really caught it. Now let's discuss how she managed to infiltrate this data. So they had a misconfigured WAF, which led to a server-side request forgery, from which she got access to the IAM credentials, and through that she got access to over 700 S3 buckets. The time to detection for this was about 4 months, whereas for her it was just a few hours of work. And the striking thing is she didn't really need a 0 day or anything. She just needed one misconfigured firewall and one overprivileged role. That's it. Now I'll go through the attack flow of the breach. So first she found a misconfigured WAF, the web application firewall that's supposed to block the malicious request, but this one allowed for server-side request forgery. This basically means that you can trick the server into making HTTP requests on your behalf. After this, she pointed that SSRF at 169.254, 169.254. It's the AWS instance metadata service. This is a local link address that every EC2 instance can reach. It's designed for the instance to discover information about itself, such as the region, instance ID, and most critically, the IAM credentials. With this, the IMDS returned temporary credentials, an access key, a secret access key, and a session token. Now, these are the same tokens that the EC2 instance uses to talk to the AWS services. And no authentication was really required to get them. If you can reach the endpoint, you get the keys. And this IAM role with these credentials, they had access to the S3 buckets way more than the application really needed. She used them, went ahead and boom, downloaded data from over 700 buckets from a totally different machine, completely different network. Once you get the credentials, those credentials really work from anywhere. And this was not any malware, it was no multi-factor authentication bypass, no 0 day, just machine identity abuse. We had one overprivileged IAM role and just one missing network control. Now, I'd like to discuss what really failed here. First, the WAF was misconfigured. It should have had the SSRF protection, input validation for the outbound requests. Now, if your firewall is allowing a web app to call 169.254, that's a configuration failure. Secondly, they were running IMDS v1, which required no session token. The V2 adds a put request requirement, so a simple SSRF attack like this can't do that. And all it takes is just one AWS CLI command to fix it. Thirdly, the role was overprivileged. The application needed access to maybe a handful at max of S3 buckets, yet it had access to over 700. The old principle of least privilege would have just contained this. Fourth, nobody was monitoring the IMDS access. There was no logging, no alerting. The metadata service was being called and nobody really knew about it. And fifth, the dwell time. 4 months from March to July. She was exfiltrating data for 4 months before someone, maybe out of their goodwill, tipped them off on Twitter. And every single one of these things are detectable and preventable, and that's what I'd like to show you today. So, what are the non-human identities? That is anything that authenticates without a human in the loop. These can be your API keys, your IAM roles, your CI/CD tokens, the Kubernetes service accounts, your AI agent credentials, the GitHub personal access token your pipeline uses, that's a machine identity. That IAM role that your Lambda service assumes, that's an NHI. The OpenAI API key that your agent calls, again, NHI. So these require no passwords. You cannot enforce MFA, and there's no human in the loop. Now, in most organizations, the NHIs outnumber human identities 50 to 1. So for 50 tokens, API keys, there's one human. And with the widespread use and adoption of AI agents, this ratio is accelerating further. Every agent you deploy just adds more machine identity, more API keys, more service accounts, a lot more attack surface for sure. Now, these identities don't really have multi-factor authentication. They are rarely ever rotated. And once a developer leaves, the HR team does a full offboarding and stuff. But are their API keys removed? Are those rotated? And these are all invisible to your IAM team. We audit human access every quarter, but can you even recall when your organization last audited your service accounts? Now, let's discuss how the NHI attack kill chain works. We first have the discovery phase where we discover what .env files are there, what credential files are there. That leads to next credential theft. After that, we do escalation via overprivileged roles and permissions. Once that is done, we do lateral movement across cross services, then establishing persistence, and finally gaining infrastructure access. This is like a normal C2 chain, but just for the NHIs. Here I have built 29 attack scenarios for the test bed across 6 progressive levels. This is a full kill chain from finding the credentials to owning the entire infrastructure. Now let's do a short deep dive into the IMDS. IMDS is like leaving your house keys under the doormat or maybe the flower pot. It works great until just someone comes and looks around. The IMDS service for AWS lives at 169.254.169.254. It's a local link address baked into every EC2 instance. It's designed so that the instance can discover its own configuration, region, and so on, but it also serves the IAM credentials. These are temporary access keys that lets the instance call the AWS APIs. The problem here is no authentication. So if you can reach that IP, you get the keys. And you see the code on the screen. It's basically just two curl commands to run. You first find out what role is there and you just grab the credentials. Done. With V2, there's a session token requirement. You first need to have a put request, but in most places, IMDS V1 is still the default. Now, for the attack flow, the attacker first uses SSRF to reach your app, point it to the metadata service, get the temporary credentials, and uses them from their couch. Can be a different country, wherever. It's your legitimate IAM credentials. Now, I'd like to do a short demo on how this works. I have recorded this yesterday just for the brevity of time. First, I would like to check if the IMDS service is up. I'll just do a simple curl. Yeah. You see the IAM folder is accessible from there. Now let's see what's in there. Boom. That's the role name for the IAM. And if I just curl that straight up, you see I can get the access key ID, the secret access key, and the token. That's it. 3 simple curl commands, and these credentials work from anywhere. You can just copy them, go home, and access from your AWS account. Now, how do we detect this IMDS abuse? This is the full pipeline with 3 different log sources here feeding into the decoders. Then we have the parent rules, then the custom non-human identity rules. Just by the way, notice those orange warnings in the diagrams. Those were the gaps that I found and fixed during the validation. This rule 100658, it was matching a wrong field, and the SS polling output actually needed a different parent rule. These were caught in testing, so before pushing anything to production, please just test stuff out. Now, here I have 9 rules across the big 3 cloud providers, AWS, GCP, and Azure. It's the same attack pattern, 3 different metadata services. Now, your AI agent most likely has HTTP request capability. So what if someone just tells your AI agent, fetch me the content from 169.254, blah, blah. That raises a whole new attack surface, and with the prompt injection, and if your AI agent can access, make HTTP requests, it's an SSRF risk. If it can read files, it might expose the credentials. If it can execute code, you can have arbitrary code execution, API calls, privilege escalation. Every tool that you give to an AI agent is a potential attack surface. And prompt injection simply turns these tools into weapons. Here, the agent becomes an unwitting proxy for the SSRF attack. It is fetching the credentials on the attacker's behalf. It is the same chain. You just ask the AI agent. It runs those 3 curl commands on your behalf, and there. It has no idea. It's now your accomplice. So for this, I have written 11 dedicated detection rules for AI agent attacks. For prompt injection, it's being detected 2 ways, both by pattern matching as well as decoder based. For tool use, SSRF, context poisoning, and MCP tool abuse, these are all detectable. In 2019, Capital One was breached by a misconfigured web app. In 2026, SSRF is going to come from inside your own AI agent. Now, if you're thinking like this sounds like OWASP, you are right. The OWASP top 10 for LLM actually lists these exact risks. The LLM number 1 is prompt injection, and excessive agency is number 6. Here's the thing, 7 of the 10 OWASP LLM risks are detectable by using plain old SIEM rules. You don't really need a new category of tooling, you just need the right rules. So far, supply chain, vector embedding, as well as misinformation, these are risks that cannot be detected with a traditional SIEM. Now, I'd like to do a short demo on how we are doing it and detecting it. So this is my Wazoo dashboard. As you can see at the moment, they are just basic data. Let me filter for the AI agent. Yeah. Last alert that came in was over 10 minutes back. Now let me just quickly switch to the terminal and run the commands. Yep. As you can see, the IAM roles, these have excessive permissions here. Now let me switch back to Wazoo. So the polling takes place approximately every 15 to 30 seconds. So there is a slight delay. Yeah, yeah. So now you can see rule 100853, it fires at level 12. This is when the parent IMDS access rule is triggered and the process name matches for an AI framework such as LangChain, Olama, etc. After this, you get the other alert that is for 100953. This changes to the credential access at level 15. This is when an NHI AI SSRF event, the previous one, is followed immediately by an AI credential access event from the same source, proving that the earlier alert was not a false positive, but rather it's a multi-stage attack chain. This is the same attack as before, just a different proxy. And yeah, it's detectable without any other new tooling. So the way we are detecting this is we have 4 branches, each with its own log source path. For branch A, shell spawning, when the AI agent spawns a shell process, audit D catches it. For branch B, that's credential file access. If the agent touches a .env or a proc environ file, it's alerted. Branch C prompt injection is caught both in the web server logs as well as in the agent's own logs using our custom decoder. For branch D SSRF, when the agent's HTTP tool hits IMDS, the alert is generated. Uh, the orange markers are here to show the gaps we found. For example, FIM actually does not include process information. So for credential detection, I switched it to audit D. Real world validation is very important. Now we have seen the attacks, same attack, both traditional and AI powered, but there's another frontier that I would like to show to you. So the next frontier for workload identity is SPIFFE. It's the Secure Production Identity Framework for Everyone. It's a cloud native foundation graduated project. It's how cloud native systems are moving beyond static credentials. So here, every workload gets a cryptographic identity, an SVID, that's a SPIFFE verifiable identity document. These are automatically rotated. These are short-lived, so there are no secrets to manage. Now, this sounds really perfect, right? But last week itself, aviator Gerzi from CyberArk, now Palo Alto, he demonstrated at Nullcon how attackers can actually bend the SPIFFE identity model without really breaking it. I'll be referring to some of the research by Aviator Gerzi, and later on I shall be reposting his blog and his findings on LinkedIn. So for the SPIFFE Spire attack surface, there are primarily four patterns to know. First, for selector spoofing, Spire is the server that generates the SPIFFE SVIDs. So Spire uses selectors, that's your process UID, your Kubernetes pod name, Docker labels to decide who gets which identity. Some selectors such as the Kate's node name, these are trivially spoofable. Second is with harvesting. The Spire agent exposes a Unix domain socket. If you escape a container and reach that socket, you can basically harvest every workload identity on the node. 3. Delegated identity API abuse. Workloads authorized for this API can impersonate every other workload the agent manages. It's kind of like the master key itself. Fourth, the trust bundle poisoning. In federated deployments, if someone injects a rogue CA into the trust bundle, and now your forged identities are actually accepted as legitimate. Well, the good news here is that every single one of these are detectable. I have added 21 detection rules specifically for SPIFFE and Spire attacks. So let me show you how the selector spoofing attack works visually. Stage one is once the attacker gains admin API access, they steal the join token, expose socket, or via an RBAC bypass. Stage two, they create a rogue registration entry with the same selector as a legitimate workload. Now the Spire agent fetches the SVIDs for matching selectors. It has the same PID, same UID, but now it gets two identities. The Spire agent itself can't really tell the difference. At stage 4, the attacker holds a valid SVID for someone else's workload. And with this now, they can do lateral movement via mutual TLS impersonation. Let's do a demo on the SPIFFE selector spoofing. I would like to first filter out for our Kubernetes agent. Yep, no alerts yet. Let me check if the Spire server is up. Yep, Spire server is running. Now we'll create first a legitimate workload entry. Yeah, any process running as UID 1000 gets the identity SPIFFE example.org web frontend. This is like normal operations. Wazoo should be detecting this as rule 101020. It's a custom rule at level 12. Now this is the attack. As you can see, both have the same selector, that's your Unix UID 1000, but a completely different SPIFFE ID. Any process running as UID 1000 now gets both the identities. This is the spoofy attack that Aviator Gerzi demonstrated at Nullcon. Yeah, as you can see, when we search for the 1000 ID, we are getting two workloads. So yeah, one process with two identities, the Spire agent can tell the difference. It now issues SVIDs for both the web frontend as well as the workload evil to the same process. Now, yeah. The full detection workflow is that we first receive the registration entry for the first one, that's your the legitimate one. Second one would be for weak selector detected, again at level 12. And the third one is the level 14 confirmed multi-identity multi-identity per PID. These are just three rules for this one attack narrative, and we can track it from the entire entry creation down to confirmed identity spoofing. Yep. So here's how we are detecting this. The Spire agent debug logs stream JSON. It has the PID SPIFFE ID method. Our Python script here monitors, runs every 60 seconds with a 5-minute sliding window. It monitors which PIDs have which identities. So when a PID accumulates two or more distinct SPIFFE IDs, that's when it's confirmed spoofing. That's the level 14 rule, 101007. And when a SPIFFE ID makes, when a PID makes 10 plus SVID requests, that's credential harvesting. That's definitely not a healthy Kubernetes service. That's at level 12. And we have at under 60 seconds, we have from the log to a actionable SOC alert, preferably even straight to your ticketing service. So this is the actual detection algorithm for the PID identity tracking. Each Spire log entry updates a PID tracking table. That's a dictionary of PID to set of SPIFFE IDs. For this, we maintain a 5-minute sliding window. It takes the decision one, whether, whether this PID has two or more distinct identities. If yes, it goes to the red path. That's the red path for critical alert, confirmed selector spooking. No comes down to decision two. Has this PID made 10 or more SVID requests? If yes, that's the yellow path. High alert for high burst detection for possible credential harvesting. This sliding window analysis catches what static sigma correlations cannot. It requires stateful tracking to be done across time. Now, let's talk about why all of this detection matters just beyond security. That should be your primary concern, but even if not. So, before I show you the detection rules, let's just see what it means beyond just catching the attackers. The EU AI Act Article 12 states automatic recording of events for risk identification. This becomes a law in August of this year. That's 5 months from now. ISO 42001 states that monitor, measure, analyze your AI systems continuously. And the NIST AI RMF, and I'm quoting this directly, alerts should be in place when anomalies are detected. From MITRE Atlas, we have 15 tactics and 66 techniques for adversarial AI. 70% of these mitigations map to existing security controls. Every major framework basically says the same thing. Monitor your AI in production. Your CISO is going to ask how you are doing this. What we are about to see now is the answer. So for the EU AI Act Article 12, the Wazoo agents, they'll be doing the continuous event monitoring and logging, that's covered. For ISO 42001, we have 100 plus detection rules. These will be doing the real-time pattern matching and anomaly detection. And as for the NIST AI RMF, the correlation rules, that is your multi-chain, multi-stage attack chains, these will generate the correlation rules and generate the alerts. For the MITRE Atlas, we have 92 Sigma YAML rules and 100 Wazoo rules. These are compliance-ready detection. We have 30 plus MITRE attack techniques mapped. You can use the Sigma YAML files to deploy to any SIEM, Beats, Splunk, Sentinel, Chronicle, whichever flavor suits your palette. Now, one thing I believe you might be thinking, and even I did have the same thought, detection rules, plain old boring regex pattern in 2026. Shouldn't we be like using some ML based anomaly detection? Well, let me try to make a case for the plain old rules. First, they are deterministic, unlike your black box AI. You give it an output, it spits a, you give it an input, it spits out an output. No one knows what's going down there in between. Probably not even the teams at Anthropic and OpenAI. With the deterministic rules, with the same input, we have the same alert every time. There's not going to be any model drift, no retraining, no surprises. And these are auditable. A regulator can come read an XML rule. I'm not sure if and some of you have had to deal with an external auditor, but try explaining how a neural network works to them. And these are portable. With one Sigma YAML, you can deploy to 5 different themes in minutes. And these are fast. There's no inference latency. The pattern matching takes just microseconds, and there's no fancy GPU and ever increasing price of RAM needed for this. And these are as well as composable. The chain parent rules to the child rules to the correlation rules. You can build the entire attack narrative from the individual signals. These are testable as well. We have achieved 96.6% end-to-end detection coverage validated by automated tests in our CI/CD pipeline. You don't need an AI to catch AI. You need good, well-written rules. The rules and the AI/ML aren't really competitors. They are complementary. But I would say the rules come first. They form your foundation. Start from there. For this, I'm using Wazoo here. It's an open source theme with agent-based monitoring. These agents run on the servers, hosts, and can do active secret scanning, connection monitoring, and syscall auditing. The detection logic itself, it's theme agnostic. Everything I showed you here, it can be converted for Splunk, Sentinel, Elastic via the Sigma YAMLs. If someone from Wazoo is seeing this, they want to give a sponsor, I'm more than willing to talk. So, the custom detection rules as I was talking about. I've built 100 custom rules across the following 9 categories, from credential discovery, cloud metadata abuse, Kubernetes security, CI/CD pipeline attacks, AI agent anomalies, secret pattern detection, the SPIFFE Spire workload identity, and bidirectional correlation rules that chain the signals together, regardless of what order the events arrive. And 30 plus MITRE attack techniques are covered. Every rule is mapped to the respective MITRE attack technique. Now, let me show you how the detection pipeline looks for each of the following rule groups. This is for credential discovery. So we have 9 credential file types being watched by auditd as well as FIM. We have .env files, AWS credentials, SSH keys, vault tokens, and so on. The final correlation rule, that's the one in red, 100609, this rule fires when 5 or more credential files are accessed in 60 seconds from the same source. That is definitely not a developer, and yeah, no chance that's even even the 10x engineer in your company. That's definitely a harvester. For Kubernetes, we have two detection branches, file access and command executions. SA tokens and host path abuse on the file side. kubectl, auth-canI, get secrets, container escape tools like ncenter, chroot, and unshare on the command side. I'll be sharing the slides on my GitHub later on. You can get the details from there as well. For the CI/CD token detection, we have GitHub tokens, CI job token, npm actions runtime token. These are all pulled from the environment variables. Along with this, FIM monitoring of the runner credential files and the pipeline config modifications are all being monitored here. So for secret pattern detection, we have two paths, and this is important. The first path is when FIM detects a file change and can match the patterns in the diff output. But that's only when the report changes is enabled. In the second path, our custom scan script actively greps the credential files. FIM alone cannot scan the static file content. The active scanner is there to bridge this gap. We are covering 15 secret patterns. We have AWS AKIA, ASIA keys, OpenAI SK keys, GitHub PATs, JWTs, and a lot more. You can see that there. Yep. And for the same detection logic, three formats. We have the Wazoo XML for the native rules. We have the Sigma YAML ones for portability, and you can get these auto converted to the Splunk SPL via PySigma. These 92 Sigma rules are ready to be deployed to Splunk, Sentinel, Chronicle, whatever. Your theme, your format. You can take this home and you can probably put it in your workload tomorrow itself. Now, one key differentiator here is the correlation rules. These are to catch the campaigns. Individual rules themselves, you can catch individual techniques, but as attackers, one might know you don't use one technique. They chain them together. Now, that's where the correlation rules come in. So for rule 950, that is your IMDS plus credential theft, that's a level 13 rule. After that, you have an AI agent SSRF along with credential access, that's a level 15. You have more than 5 NHI events from the same source in under 10 minutes, that's level 15. The rules 960 to 964, those are our reverse correlation ones. They ensure that detection happens regardless of the event order. So it is if event A happens, then event B, that's detected. If event B happens, then event A, that's detected as well. And here's what it makes it robust. Also, level 15 means it's confirmed as a multi-stage attack chain. That's when you get a 2 a.m. phone call. So yeah, this is the bidirectional correlation on how the order is done. And this is very important as if you only have it for event B to fire after event A, you might miss out on attacks. These can go undetected. So here's the full correlation architecture. We have 9 source rule groups feeding into these 5 bidirectional correlation pairs, plus the catch-all rule of 954, when 5 or more NHI events from the same IP hits in 10 minutes. And see that orange annotation there? The original correlation rules for this were one directional. So if IMDS access happened before credential theft, the alert fired. But if credential theft happened before, then IMDS, it was missed. So that's what bidirectional means in practice. not just forward chains, we have it for both directions. So yeah, this is how a rule looks like. So as you can see, the one on the bottom, the 651, that's for IMDS credential theft. It's the child rule of 650, the which fires whenever IMDS is accessed. When a child sees that IAM security credentials are part of the request, that fires the 651 at the level 12. We are mapping it to the respective MITRE techniques, and these are grouped as credential theft. These are simple to read and auditable. And if you might notice, the parent rule fires for both the audit the syscall monitoring as well as for active connection polling. The dual source detection at the base layer. So whenever when either source detects IMDS access, the child rule catches the credential endpoint specifically. So here's how it gets powerful. We have the IMDS one at level 8. That's a daily review item. It's most likely legitimate. But when the child rule sees the credential endpoint, now that's a level 12. That becomes a 1 hour response SLA. So when you then correlate this with file credential access, that's a level 14. 5 or more NHI events from the same source, level 15. That requires your immediate response under 2 minutes. Individual rules are great to catch techniques, but the chain, those catch the campaigns, and the campaigns catch the APTs in your system. Now I'll just do a one final demo. So here's our Wazoo dashboard. We have the 5 agents monitoring the different environments. We have the vulnerable app, Kubernetes node AI agent. No alerts, no high level alerts as of yet. Let me filter for the cloud workload. And yeah, last alert is over 5 minutes ago. This is the same IMDS attack, but this time it's from the inside the cloud workload container. This is how the real attacker would after gaining the initial access. Yeah, we enumerated the IAM roles. That's the reconnaissance phase. Cool. We already have an alert. IMDS access is detected. This is at level 8. These are for your SOC team to review on a daily basis. Now let's run the role and get the credentials. Yep, there you go. It's at level 12 rule for credential theft. This is our custom rule and it's auditable. An auditor can look at this and they can understand exactly what it's detecting. I would suggest three fixes actually. First, enforce IMDS v2, blocks the simple SSRF. Secondly, rotate your credentials immediately. In production, you do this within minutes. And thirdly, and the point of this whole talk, me making the journey over here from India across the Gulf in the middle of a war, have the detection rules in place so that you can catch it in real time, not from Twitter and definitely not 4 months later. So yeah, we would like to look for the access patterns, secret patterns, as well as peer sockets, and if any token is being accessed. So here's what you can do this week, not next quarter. Let's sort it out within a week. Firstly, audit your NHIs. Just count them. I bet you'll be surprised. You can use Trufflehog against your repos to find exposed secrets. I believe you'll get something or the other. Enable IMDS v2. It's just one CLI command. And review the CI/CD permissions. What can your pipeline actually access? Are you sure you know what it is? For long term, I would say 5 things. Secrets management. If you're still using .env files in production, please stop. It's a request. Follow the principle of least privilege. Every machine identity should have exactly what it needs, nothing more. Keyless is the future. GitHub Actions, AWS, GCP, they all support OIDC Federation. And have a inventory of your NHIs. You need visibility. You cannot secure what you can't see. And yeah, have AI agent guardrails. If your agent can make HTTP requests, it should have a URL allow listing. So here's how you can see. Here's the before on the top. Bare request.get. Any URL, any host, there's no validation. And after we have a blocked host list, HTTPS is required and URL validation. Simple and effective. This isn't really rocket science. It's just input validation. We have been doing this for web apps for 20 plus years. It's the same principle just for the AI agents. So building detection. Deploy agents on the workloads. Write custom rules for your environments. Correlate across sources. CloudTrail plus Wazoo plus GitHub audit logs. These actually work pretty well. And generate alerts for the anomalies. And just by the way, this satisfies all the ISO clause 9, then EU AI Act Article 12, as well as the NIST AI RMF. Continuous monitoring of AI systems in production. You are not just improving security, you are meeting compliance requirements. And yeah, let me be clear about what you'll be getting from this testbed. Later on this week, I'll be releasing it on GitHub. Currently on GitHub, it's the initial preliminary version. You will get 100 detection rules you can drop into Wazoo, 92 Sigma rules that can be converted for your scene, 29 attack scenarios for purple teaming exercises, and full MITRE attack mapping. Compliance coverage for NIST, EU AI Act, and ISO 42001. This is not just a demo, it's a production detection library, and I'm going to make it open source, take it home, deploy it, and maybe hopefully even contribute to it. Yeah, so I'd like to hear back from you in 3 weeks' time. For the first week, deploy the rules, any platform, and your choice of theme. In the second week, tune the thresholds for your environment, review the false positives, adjust the alert levels. And in the third week, wire this into your SOC playbooks and incident response procedures. And in your CI/CD pipeline, please run the validation script. It tests for detection coverage automatically. And NHI detection coverage in production within 3 weeks. This is not a promise. This is the plan. Key takeaways from this talk would be NHIs are your biggest blind spot. They are at the ratio of 50 to 1, and with more AI agents, it's growing much faster. Assume breach, detect early. You cannot prevent everything, but at least you can catch it in minutes instead of months. Third, least privilege is non-negotiable. Every NHI, every time, no exception. For your AI agents need the guardrails. Every tool you give them is a new attack surface, and compliance demands it. ISO, NIST, AIRMF, it's going to be, and the EU AI Act is becoming a law in 5 months. every major frameworks requires the continuous monitoring of AI systems, and detection rules is how you do it. Yeah, this week, just do this one thing, audit your NHIs, just count them. You can run these commands, you can take a picture if you'd like. You find your IAM roles, your access keys. I guarantee you will find something surprising. Uh, these are the resources for this talk, and you can access it in GitHub. Towards the end of next week, I'll be finalizing it and publishing the entire rule list. Any questions, anyone? Okay, I guess we are good then. Uh, you can connect with me. That will lead to my link tree. You can find my email, LinkedIn, everything there, as well as the GitHub links. This feedback form is from NDC. You can give a feedback on your thoughts on the talk, and I would appreciate it. I guess everyone's feeling a bit drowsy now. Probably need a strong cup of coffee. Thank you everyone for attending.